while we are journeying into mechanics, one very important and critical element that we will encounter very often in problem solving and otherwise is the inclined plane element. And over a period of time, so many variants, so many variations around the inclined plane have emerged. And it is important to consolidate all inclined plane knowledge in one place. It's important that we take delta steps and address all issues in all variants that we see in inclined planes. My objective in a few sessions is to give you a complete, holistic, comprehensive understanding of inclined planes. We start with an inclined plane whose surface is smooth, and we will initially look at an inclined plane that is at rest. Inclined plane not moving, a fixed inclined plane. And slowly I'm going to release bundles of knowledge. From this point, a fixed inclined plane, I'm going to allow the inclined plane to move. And then look at the moving inclined plane in very many ways. Let's see what happens. All right. So here's our inclined plane. And there is a mass small m, a particle of mass small m, resting on the surface of a smooth inclined plane. So first things first, let's try and understand unequivocally, without ambiguity, the forces acting on small m. We are going to draw the free body diagram of the particle resting on the inclined plane, and we are going to draw the free body diagram of the inclined plane itself, right? So first of all, let me look at this small m. What about this small m? What are the forces acting on small m? Very clearly, there is mg downwards. Vertically, this is the vertical direction, right? And there is normal reaction n, which makes an angle theta with the vertical. I hope you realize all these angle dispositions. If this angle is theta, if the inclined plane makes an angle theta with the horizontal, a normal to the inclined plane will make an angle theta with the vertical. This is the vertical direction. This is the vertical direction, right? Or you could have looked at it geometrically this way. This is theta, this is 90 degrees, this is 90 minus theta. So this will be theta, and then vertically opposite angle theta, and so on and so forth, right? And then we have n acting this way, perpendicular to the plane. That makes an angle theta with the vertical. So only two forces acting on small m. What are the two forces? mg like this, and n perpendicular to the plane. Yes or no? Now, since n and mg are in different directions, it makes sense, in order that we could deal with them in an organized manner, it makes sense to resolve all these forces in two mutually perpendicular directions. It makes sense to resolve these forces in two mutually perpendicular directions. What we could choose as two mutually perpendicular directions are, we could choose a direction parallel to the plane. This is the parallel direction. And a direction perpendicular to the plane. This is the perpendicular direction, perpendicular to the plane. So all forces in a certain sense can be consolidated in these two mutually perpendicular directions, or it could be any other choice, which is all right. Now, in the perpendicular direction, let me look at the perpendicular direction perpendicular to the plane. I could have resolved mg as mg cos theta perpendicular to the plane, right? And parallel to the plane would be mg sin theta. So here we have set of forces acting on small m, normal reaction from the inclined plane, perpendicular to the plane, and then mg, which could be replaced by two other forces, which is mg cos theta perpendicular to the plane and mg sin theta parallel to the plane. Yes or no, right? Now, the inclined plane side of the story. So, on the inclined plane, what are the forces? It's weight, capital Mg acting downwards, normal reaction R from the ground. Now the inclined plane exerts on small m a normal reaction n this way, right? N this way. The inclined plane exerts on small m n this way. So as a consequence of Newton's third law, small m will exert on the inclined plane a normal reaction n this way. A normal reaction n this way. So then on the inclined plane, what are the forces? A normal reaction n, and who exerts this normal reaction n on the inclined plane? Small m, that is this particle on capital M. And then of course there is weight of the inclined plane, capital Mg, and there is normal reaction R. Now again, if you really think about it, In the vertical direction, the inclined plane has no acceleration. So n cos theta mg must balance r. R is a self-adjusting force, right? So R then, for the inclined plane, R then is like a capital Mg plus n cos theta. Capital Mg plus n cos theta, right? In the vertical direction. Now, do you realize this n sin theta is unbalanced? And what would it want to do? It would want to cause the inclined plane to accelerate leftwards. It would want to cause the inclined plane to accelerate leftwards. So something has to prevent it from accelerating leftwards. So what has to be done is, to keep the inclined plane fixed, we would have to counter n sin theta. We would have to counter n sin theta. So this n sin theta could have been countered, let's say, if I had placed it against a wall, for example. If I had placed it against a wall, for example, then this n sin theta could have been countered. Or if the inclined plane was placed on a very rough surface, then the tendency of the inclined plane to move to the left owing to n sin theta would have been cancelled by frictional force acting on it to the right. Yes or no? Static friction acting to the right would have countered. One way or the other, by some means, we are preventing n sin theta from producing an acceleration on the inclined plane. The inclined plane remains unaccelerated, right? So this is the situation that we are talking of now. So unaccelerated inclined plane, fixed inclined plane, by some mechanism, by some mechanical mechanism, n sin theta is countered. Now, look at small m, small m. Would you not want to believe that in a direction perpendicular to the plane, fixed plane, small m has no acceleration, because if in the fixed plane small m had an acceleration perpendicular to the plane, it is going to lose contact with the plane, right? So no acceleration in this direction of small m. That means net of all forces in this direction is 0. That means n must be equal to mg cos theta. But this is only for a fixed inclined plane. Only if the inclined plane is fixed will the normal reaction be equal to component of weight, which is mg cos theta. If the inclined plane was moving, we'll see very shortly that n is not mg cos theta. Now, so on this particle, what's the only unbalanced force acting on this particle m? That's mg sin theta. That's mg sin theta is the only unbalanced force acting. And what does this unbalanced force do? It produces an acceleration a parallel to the plane. It produces an acceleration a parallel to the plane. So mg sin theta produces on the particle an acceleration a parallel to the plane, which means a then will be g sin theta. So on an inclined plane that is fixed and that has a smooth plane, smooth inclined surface, if a particle moves down the plane parallel to the plane, then its acceleration is going to be g sin theta. That's the story of a fixed inclined plane. What I'm going to next migrate to is I'm going to bear with the consequences of n sin theta not being balanced. That means I'm going to look at how n sin theta causes this to accelerate, and if n sin theta is left free to accelerate this, what would be the acceleration developed by the inclined plane on capital M? This is what I'm going to explore next, right? But I hope all of you understand this very basic premise of a fixed inclined plane whose inclined surface is smooth. The acceleration of a particle parallel to the plane is g sin theta. There is no acceleration perpendicular to the plane. Acceleration perpendicular to the plane would have caused the mass small m to lose contact with the plane. Yes or no? Thank you so much. As a follow-up from the previous situation where I looked at a fixed inclined plane, I'm now going to let the plane do what it wants to. I'm going to make it rest on a smooth horizontal surface. The inclined plane itself is smooth and there is a particle of mass small m moving along the plane, right? I'm going to have a detailed digression of this, and we'll look at it in very many ways. All right. So first things first. this is a particle of mass m resting on the inclined plane. What are the forces acting on it? There is mg, Mother Earth, and there is normal reaction from the inclined plane perpendicular to the plane, right? These are the two forces acting on small m. That far and no further. I'm assuming that this surface is smooth. Of course, if required, we could resolve mg perpendicular to the plane as mg cos theta and parallel to the plane as mg sin theta. But that's it. I mean, we could resolve it in other ways too. But this is one of the ways we could resolve mg. We could, if we want to deal with two standard directions, parallel to the plane and perpendicular to the plane, this is one thing that we could have done. Now, look at the inclined plane side of the story. What are the forces acting on the inclined plane? This is the inclined plane. There is capital mg acting downwards. There is normal reaction from the ground acting upwards, right? And if the inclined plane exerts on small m, n like this, small m will exert on the inclined plane a normal reaction n like this, right? Which could be resolved as n cos theta downwards and n sin theta leftwards. Yes or no? Then from the ground, there is a normal reaction acting on the inclined plane, preventing the inclined plane from having a vertical acceleration. So essentially then what happens from the inclined plane perspective is that mg and n cos theta balance r. Mg and n cos theta balance r. R is a self-adjusting force. It manipulates itself in a manner that there is no net acceleration of the inclined plane in the vertical direction, right? That's as far as this is concerned. But what about n sin theta? Now, there is nothing to counter n sin theta. There is no friction. Everything is smooth. And there are no other forces acting. So, n sin theta stays put as an unbalanced entity on the inclined plane. Capital M, right? This is capital M. So, n sin theta produces on capital M a leftward acceleration, capital A. A leftward acceleration, capital A. Right? So the inclined plane has a leftward acceleration capital A owing to the influence of this n sin theta. Yes or no? I hope all of you are in tune with me and are in sync with whatever I'm saying. Right? Now, if you are an observer sitting on the inclined plane, what would you observe about this particle? You would observe that the particle is sliding along the plane. That means, if you observe that the particle is sliding along the plane, what would you want to conclude? You would want to conclude that the relative velocity of small m, with respect to capital M is parallel to the plane. The relative acceleration of small m with respect to capital M is parallel to the plane. There is no relative motion in this direction. Along the common normal, if there was relative acceleration or relative motion of any kind, then it would result in loss of contact. There is no loss of contact. So, relative acceleration perpendicular to the plane is 0. But there is non-zero relative acceleration down the plane. An observer on the plane would not find this particle to have an acceleration perpendicular to the plane, but would observe an acceleration small a parallel to the plane. So this is the relative acceleration of small m with respect to the inclined plane, and this relative acceleration, at least we know its direction, it's parallel to the plane. And the fact that there is no relative acceleration perpendicular to the plane between the inclined plane and this mass m is because of a wedge constraint. That's the condition for it to maintain contact. So no relative acceleration in this direction. So whatever the inclined plane has an acceleration in this direction is also the acceleration of small m in this direction, so that the relative acceleration condition equal to 0 is preserved. So on small m, this is small m. What are the two things that you are going to see on small m? One, there is relative acceleration like this, right? That is a that is a inclined plane observer's perspective, this A. This is not, however, the acceleration of small m in the ground frame. No, this is not the observation made by a ground observer. What is this? This is the observation made by the inclined plane. The inclined plane observer reports that small m has an acceleration like this. Yes or no, right? So this is only relative to the inclined plane. But what about the inclined plane itself? Is it fixed? No, it has an acceleration a to the left. So this is the observer's acceleration. And what is the observer reporting? This. So if I add the observer's acceleration to the relative acceleration it is reporting, see, relative acceleration added vectorially to the acceleration of the observer, that means capital A and small a, would give me what? Acceleration of the particle m in the ground frame. So in the ground frame, what would you see? In the ground frame, you would see a resultant of the relative acceleration of small m plus the acceleration of the inclined plane. Inclined plane reports this. Inclined plane reports this. So the reporting of the inclined plane plus whatever is happening to the inclined plane will give me a ground observer's framework. If this was a ground observer, then the ground observer would think that the resultant of the relative acceleration plus the acceleration of the observer, which is the inclined plane, A and capital A, this angle is theta, as you can see, this angle, this is A, this is capital A, this angle is theta, as you can see, would give me the acceleration of the particle m in the ground frame. In the inclined plane, small a. In the ground frame, resultant of small a and capital A, that's the story in the ground frame. Yes or no? Right? I'm going to build on this. Once you understand this clearly, small a henceforth is what? Acceleration of small m with respect to the inclined plane. Obviously, it's along the plane. And capital A is what? Acceleration of the plane. If I add these two, this is the observer and this is what the observer is reporting. The kinematic status of the observer and its reporting will together give me what? The absolute acceleration of the particle, that is the observed, right? I'm going to build around this. So I'm going to write equations of motion for small m. I'm going to write equations of motion for small m, keeping in mind that I know whatever forces acting on small m will produce a net effect, which is the resultant of small a and capital A. The net effect of small a and capital A would be the effect of all forces acting on small m. Now, whether I choose to resolve forces acting on small m perpendicular to the plane and parallel to the plane and write equations of motion of small m parallel to the plane and perpendicular to the plane, or I resolve forces vertically and horizontally and I look at the effect of these two in a horizontal sense and in a vertical sense, that does not matter. That is only cosmetic. But in principle, this is what I'm going to deal with. This being the effect in a ground frame perspective, small a and capital A put together is a net effect in the ground frame, and I'm going to look at forces acting on small m that will produce this effect. Cosmetically, I might do very many things, but in principle, this is what I'm going to deal with. Thank you so much. In my session that is to follow, I'm going to come down to downright equations in two mutually perpendicular directions. Aim at solving capital A, the acceleration of the inclined plane, and solving small a, which is the relative acceleration of small m with respect to capital M, that means the inclined plane. And then, of course, I could find the resultant of these two. That will give me the net acceleration in the ground frame. So that's my agenda for the session to follow very soon. Thank you so much. Bye. To eventually converge to a solution of the inclined plane problem based on some of the inputs that I gave to you, where I said A is the relative acceleration of the particle with respect to the inclined plane, which would be evidently along the plane, and capital A is the acceleration of the inclined plane itself because of an unbalanced n sine theta, which we saw earlier. Then the resultant of small a, relative acceleration with the acceleration of the observer, would give me the acceleration of the particle in the ground frame. Now, therefore, if I resolve capital A, that means I have to essentially find the resultant of small a and capital A so as to perceive the acceleration of small m in the ground frame. So I resolve capital A as a cos theta parallel to the plane and a sine theta perpendicular to the plane. right? So essentially, if I add a cos theta, a sin theta, and small a, that will give me, this resultant will give me the acceleration of small m in the ground frame, right? Therefore, in the ground frame, parallel to the plane, what's the acceleration parallel to the frame in the ground frame? A minus a cos theta. A minus a cos theta is the acceleration of small m in the ground frame. So this is all in the ground frame. Whereas a sin theta is the acceleration in perpendicular to the frame, perpendicular to the plane, as seen by a ground observer. So the ground observer sees a minus capital A cos theta parallel to the plane and capital A sin theta perpendicular to the plane on small m. That's now. So this is the effect of whatever is happening on small m. What is the cause? Okay. So what causes A sin theta on small m? All forces perpendicular to the plane will result in capital A sin theta. What are the forces perpendicular to the plane? Mg cos theta minus n. Mg cos theta minus n will cause A sin theta, right? So mg cos theta minus n will cause A sin theta, right? So that's equation 3. So equation 1 was like the inclined plane having an acceleration a, as we saw earlier, because of n sin theta. N sin theta is capital M into a, right? Now parallel to the plane, what's the acceleration? A minus capital A cos theta. And what causes that? All forces parallel to the plane, that is mg sin theta. So mg sin theta causes A minus capital A cos theta. So mg sin theta causes small a minus capital A cos theta. This acceleration. That's equation 4, right? So what I'm going to do is, I'm going to use equation 1, which is this equation, and I'm going to use equation 3, which is this equation, and first solve for n. Solve for n. Right from this equation, as you can see, I can replace n by ma by sin theta. Capital Ma by sin theta, by the way. Capital Ma by sin theta into this equation. And first I'll solve for capital A, the acceleration of the inclined plane. See what it turns out to be. So this is like a mg cos theta minus n replaced by capital Ma by sin theta equals small ma sin theta, right? I transpose this on this side. I get mg cos theta equals a into, if I add these two, capital M plus small m sin square theta divided by sin theta, right? That's what happens. A then turns out to be mg cos theta sin theta, mg cos theta sin theta divided by capital M plus small m sin square theta. That's the acceleration of the inclined plane, mg cos theta sin theta by capital M plus small m sin square theta. Good. Now once I have capital A, can I not solve for small a? Can I not solve for small a? I can plug in capital A into this and solve for small a. Solve for small a. Resultant, the relative acceleration of small m in the inclined plane frame of reference. So let me go to equation 4. I cancel m, and then I have like a small a equal to g sin theta plus a cos theta. G sin theta plus a cos theta, capital A cos theta, right? Let me simplify this. Replace a by this. So when I do that, let's see what happens. Right here, a is g sin theta plus capital A cos theta. That means mg cos square theta sin theta. See, g cos, I'm saying a cos theta, this into cos theta, so mg cos square theta sin theta divided by capital M plus small m sin square theta, right? See what happens. From these two, I'm going to take g sin theta common. So if I took g sin theta common from these two, if I took like a g sin theta common from these two, then I end up getting 1 plus m cos square theta divided by capital M plus small m sine square theta is what I get, right? Let's see what this turns out to be. So if I add small m sine square theta plus small m cos square theta, that will give me m. So capital M plus small m in the numerator, capital M plus small m into g into sine theta divided by capital M plus small m sine square theta. So here we have, eventually, after a lot of deliberations, after a lot of detailed analysis and discussion, we have the acceleration small a with respect to the inclined plane available to us, and the acceleration of the inclined plane as well, right? Now all that I need to do is, if I vectorially add small a and capital A, I'm going to get the net acceleration in the inclined plane frame of reference. I'm going to get the net acceleration in the ground frame of reference. Yes or no, right? So this does seem like an interesting situation to deal with. Here what I did was the basic premise of adding the relative acceleration to the acceleration of the observer, which is the inclined plane, and then looking at forces on the particles small m, this time writing their net effect perpendicular to the plane and parallel to the plane. I could have looked upon their net effect in the vertical direction and horizontal direction as well, which is what I'm going to address in a short while. Thank you so much. Bye. In the session that just concluded, I obtained the acceleration capital A of the inclined plane, right? Mg sine theta cos theta by capital M plus small m sine square theta, etc. I also obtained the relative acceleration of small m with respect to the inclined plane along the plane, right? And I said to you that the resultant of these two will give me the acceleration in the ground frame, right? And what I did was, with this basic premise of capital A and small a giving me the net acceleration in the ground frame of reference, I chose to write my equations of motion in two mutually perpendicular directions, perpendicular to the plane and parallel to the plane, right? Now I'm not going to do anything new. All that I'm going to do is, I'm going to write my equations of motion along the horizontal direction, which I'll call the x direction, and in the vertical direction, the direction of Mother Earth, and that is the y direction. And I'm going to show to you that, you know, we are not getting anything different. Why should it be different? The whole thing is very well cemented and bonded. So no matter what, if we don't goof up, we'll get the same thing, right? So like I said, the resultant of small a and capital A will give me the net acceleration. And I this time choose to look at things horizontally and vertically. So in the horizontal direction, the net acceleration in the ground frame is going to be this A resolved in this direction as A cos theta and capital A. So A cos theta minus capital A, right? A cos theta minus capital A is the acceleration of small m along the x-axis. In the y direction, it's like a sine theta. It's like a sine theta this way, right? So in the ground frame, Ax is A cos theta minus capital A. In the y direction, Ay is A sine theta, and I'm going to apply Newton's second law along the x-axis and along the y-axis based on these forces. What are the forces acting on small m? There is mg like this, and there is capital M perpendicular to the plane. And capital M could be resolved in the y direction, vertical direction as n cos theta, and horizontal direction as n sine theta. Clearly, mg minus n cos theta will produce ay, and n sine theta will produce ax. This is what's going to happen, right? And of course, like before, from the inclined plane perspective, n sine theta is capital M into a, which is the unbalanced force acting on the inclined plane, causing the inclined plane to have an acceleration capital A to the left, right? Good. So let me write equations of motion along the x-axis and along the y-axis. So along the x-axis, for small m, we have n sine theta doing the following. Acting on the mass small m to produce ax, m into a cos theta minus capital A. A cos theta minus capital A. This is what it's doing, right? That's as far as n sine theta is concerned. Uh, what about the vertical direction? Vertical direction, let's write as, so let me call this equation 3, because these were equations 1 and 2. In the y direction, I have like a mg minus n cos theta, mg minus n cos theta, and that's going to give me mass into a sine theta. That's equation 4. That's equation 4. All that I therefore need to do is to solve for small a and capital A from this equation, small a, capital A and n, from this equation, and equation 1. This is what I need to do, right? And we are not going to get anything different from what we got earlier. If I solve for capital A from these two equations, let me tell you the final result, if you allow me. I'm going to get capital A as mg sine theta cos theta divided by capital M plus small m sine square theta, not any different from before, and small m as capital M plus small m g sine theta divided by capital M plus small m sine square theta. This is what I'm going to get as capital A and small a. So this is just to make sure that you understand that, you know, all roads lead to Rome. I have not communicated anything different. It's just that, you know, I chose to be cosmetically different. But eventually, being cosmetically different doesn't mean that you're going to get different conclusions out of that. Conclusion would be the same. You might take to different routes. But as long as you're not goofing up algebraically or conceptually, then taking to any route is fine, and resolving forces along the y direction and the x direction and writing equations of motion commensurate also did the job for us. Thank you so much. I hope you're enjoying all of this, but we have not done. There is a lot of things. Next, what I'm going to do is I'm going to look at the same problem. I have written my equations of motion from a ground perspective. I've taken only real forces, n and mg on small m, the particle, and I have applied equations of motion along the x direction and the y direction and solved the problem, right? That is in a ground frame. So all my solutions so far have been in the ground frame, but I'm not averse to the idea of looking at the same problem in a frame of reference attached to the inclined plane, which would be my next agenda. Thank you so much. Bye. We're not done with inclined planes. I'm inclined to tell you more. We've dealt with the inclined plane free to move on a smooth horizontal surface, and we've obtained the acceleration of the inclined plane with a particle of mass small m coming down, falling down, sliding down the inclined plane. No friction anywhere, so far smooth. But we've dealt with the same thing in a few ways, but I'm going to now deal with the inclined plane with the frame of reference or the observer being the inclined plane itself. That means we're going to solve the problem in a non-inertial frame. The inclined plane is an accelerated frame, and we're going to solve this problem in the inclined plane. As we have seen before, the inclined plane has an acceleration a to the left, courtesy n sine theta. We've done this so many times. So n sine theta is ma. So now look at small m. We're going to look at small m in the inclined plane frame of reference. So in the inclined plane frame of reference, which is a non-inertial frame, if I have to apply Newton's second law, then what I need to do is, to the set of real forces n and mg, I need to add a force minus m times the acceleration vector of the inclined plane. So, which is very clearly small ma to the right is the pseudo force acting on the inclined plane, right? So then, together with n, ma and mg, real and pseudo forces coming together, conniving, cementing together, and what would that produce? That would not give me the acceleration in the ground frame. That is going to give me the acceleration small a of the particle in the inclined plane frame of reference, which we already know is along the plane, right? So that means the resultant of all these forces, N, Ma and Mg, is going to be an acceleration a down the plane. This is what will happen, right? That being the basic idea. I could have written my equations of motion for small m parallel to the plane and perpendicular to the plane, or I could have written that in the vertical direction and in the horizontal direction. So if I choose to deal with directions parallel to the plane and perpendicular to the plane, then what I have is parallel to the plane set of real and pseudo forces is going to be ma cos theta plus mg sin theta, ma cos theta plus mg sin theta, right? And perpendicular to the plane is going to be, as you can see, n plus ma sin theta, n plus ma sin theta, which is this, n plus ma sin theta, and there is mg cos theta like this, right? Now, there is, so these forces will give me what? Relative acceleration. But relative acceleration of small m perpendicular to the plane has to be 0, keeping in mind the wedge constraint, keeping in mind the condition so that small m maintains contact with capital M. So net of all forces in this direction has to be 0, because there is no relative acceleration in this direction. So very clearly, n plus ma sin theta must just about balance mg cos theta, right? That's as far as this is concerned. And in this direction, what do? They produce an acceleration small a. So then we have, along the plane, we have the equation of motion as mg sin theta plus ma cos theta as small m into a. Right. So using these two equations once again, along with, of course, n sin theta equal to na, this remains cardinal all the time. Using this equation, and this equation, I can once again solve for capital A, n, and small a. Capital A, like before, will turn out to be mg sin theta cos theta by capital M plus small m sin square theta. Similarly, small a will turn out to be capital M plus small m g sin theta divided by capital M plus small m sin square theta. That is what is going to happen. So, and you know, I could have solved the same problem by resolving my real and pseudo forces horizontally and vertically. In the horizontal direction, I clearly have ma plus n sin theta, ma plus n sin theta. In the vertical direction, I have mg and n cos theta. And what do? Look, the acceleration in the inclined plane frame of reference is small a, which has a horizontal component, as you can see, a cos theta, and has a vertical component a sin theta. Who's instrumental in producing a cos theta? ma plus n sin theta, right? ma plus n sin theta results in ma cos theta, right? Right? The real plus pseudo forces give me what? Relative acceleration. So relative acceleration in this direction is a cos theta, in this direction is a sin theta. In this direction, who causes relative acceleration a cos theta? ma plus n sin theta. In the vertical direction, what's the equation of motion? mg minus n cos theta equals m into a sin theta, a sin theta, a sin theta. So then I have this equation, along with this equation, n sin theta is capital M into a, giving me the values of capital A and small a. So we've learned in a certain sense how to deal with this problem in the ground framework, in the inclined plane framework, and by resolving forces parallel and perpendicular to the plane, as well as resolving forces vertically in the direction of Mother Earth and horizontally perpendicular to the direction of Mother Earth. So I'm assuming that you're getting a hang of things and that you're feeling comfortable with it. But I'm still not done. I'm going to demonstrate yet another concluding aspect of the same thing. They are all cosmetically different. They deep within, they converge somewhere. But I will demonstrate another way of handling this problem so that it gives you mental comfort dealing with these situations. Thank you so much. Bye. I'm going to present to you a closing remark on this variety. However, there are more variants on the inclined plane that I'm going to deal with, but this one variety where the inclined plane has an acceleration capital A to the left, the particle of mass small m has an acceleration small a down the plane, right? And I'm going to look upon capital M as small m as one single system, and I'm going to apply generalized second law to it. When I apply generalized second law to it, realize on a system comprising small m and capital M, there is no net horizontal force. There is no net horizontal force, which means mass small m into acceleration of small m in the horizontal direction plus mass capital M into acceleration of capital M in the horizontal direction must be 0. So if this is my horizontal direction, then if I look upon capital M plus small m as one single system, right, then generalized second law means Fx in this direction must be 0. Net of all forces. Capital M will not feature. Normal reaction between small m and capital M will not feature in this. Why? Because that's an internal force. So then, what is Fx in the horizontal direction? Generalized second law, mass into acceleration of small m in the horizontal direction. What's the acceleration of small m in the horizontal direction? As you can see, a cos theta minus capital A. Small m into a cos theta minus capital A, right? Plus mass of the inclined plane into acceleration of the inclined plane, which is a to the left, so minus a. That must be 0. That's 1. Now, let me look at small m parallel to the plane. Small m parallel to the plane. What is its acceleration parallel to the plane? Parallel to the plane, its acceleration is small a minus capital A cos theta. Small a minus capital A cos theta. And who causes that acceleration? Mg sin theta. Mg sin theta causes that acceleration. So then we have mg sin theta instrumental in doing small m into small a minus capital A cos theta. Yes or no? Does it make sense to you? Does it make sense to you? Right? If I solve these two equations, once again I can get the value of small a and capital A without having to deal with normal reaction n. So I'm going to get the same values of small a and capital A as I got earlier. But this is like applying Newton's second law on small m plus capital M together, right? And I hope you're feeling comfortable with things. You are at home and in tune with all of this. But then, given this basic look of an inclined plane, we are going to add pulleys, we are going to add friction, and we are going to do a variety of things and make you very, very comfortable with the whole notion of inclined planes. Thank you so much. Bye.